I do like just to spend some time to acknowledge the country that we meet on today. I acknowledge that we meet today on the traditional owners of the Kaurna people of the Adelaide Plains, and I recognise and respect their cultural heritage, beliefs and relationships with the land, and acknowledge that of their continuing importance today. And I'm very privileged to be standing on Kaurna land here at Concordia College. When I was asked to give the keynote, my head went into a big sort of spin. I went, oh, I could do so many different things around this theme of mathematics in a changing world. And I suppose I'm going to share some of those rabbit holes that I started to go down, and then I'll go into where I end up sort of thinking. So persevere with me while I share some of my weird old thinking as I go through. At first I went, well, mathematics has got such a rich history. And I could have explored all the different historical developments around mathematics. Perhaps just quickly turn to the people around you. Do you recognise any of these contributions to mathematics? There's some Babylonian, there's some Mayan, the Ishengo bones, apparently the oldest contributions to the mathematics world. David had it. Okay, so I could have explored the Stone Age and ancient contributions, and I think they're really valuable contributions to how we've developed mathematics over time. And I go, well, that's one part of our historical development. I could have also gone into a more of a modern era, but Mathagon has already done something like that. And we can learn a lot from how mathematics has contributed and changed over time. I then thought, well, with the development of mathematics comes pedagogy, and I could explore all the different pedagogical changes that have happened, from having 60 students in a classroom, that's a Tasmanian classroom, to using the blackboard, to going to the overhead projector, to getting really excited and using coloured things on the overhead projector, to using things like the whiteboard, the interactive whiteboards, to the mini whiteboards, to vertical whiteboards, and of course technology contributions. And I could explore how those changing practices have impacted on student achievement and engagement. And I thought, oh, speaking of achievement, we could just look at how student achievement has changed over time. And this is the International Maths and Science Study results, and we can see in purple on the right graph about mathematics achievement of Year 8 students in Australia. And I could unpack what that looks like over time and some of those factors. And then I went back to one of my research passions, and that is about attitudes towards mathematics. And once again, the International Maths and Science Study have documented how attitudes have changed over time. And attitudes to them is sort of reduced down to liking mathematics. Don't get me started on that, but we know that mathematics is more than just attitudes towards mathematics, is more than just liking mathematics. And you could look at how they have changed and the items that they've used. And we just want to note that in 2011 and between 2015 and 2019, the scale has changed. So we've got to be careful how we interpret the following results. But we could look at how students' attitudes from a Year 4 or a Year 8 perspective have changed over time. And I think the statistics tell one story, but it's only part of the story. We can see that besides 2007, where they changed the instrument that they were measuring, that generally there's a decline in students who very much like mathematics, and we can see the same kind of trend for somewhat and do not like mathematics. And over time, of the students who very much like mathematics for both Year 4 and Year 8 in Australia and internationally is changing in a sort of decreasing, with that hiccup in 2007 due to the instrument being changed. And I thought, well, what's another change that's happened most recently that is impacting us? And that is some of the changes around curriculum. We're all about to adopt the version 9 of the curriculum, and sometimes we just go, okay, the curriculum's changed, there's some different mathematical terms in this curriculum. And I just want to pull out 2 examples, otherwise, once again, this whole keynote could have just been exploring all the changes in the curriculum. So this is Year 2, and I know it's rather small to read, but one of the content descriptors is looking at recall and demonstrate proficiency with addition facts to 20 and extend and apply these facts to related subtraction. That's changed from going from year 3, so it used to be year 3, now it's in year 2, and now there's the extra addition of subtraction in that. And you go, well, that's not much. That's not much of a change. But when we unpack it, we see that in version 8.4, our previous version, there was 64 addition facts. And now with this new introduction of subtraction facts, the work from Hopkins at MERGA this year, the Mathematics Education Research Group of Australasia, she's done the maths for me, I didn't have to do it. Now it's gone from 64 facts to 304 facts, from year 3 to year 2. So that's quite a huge shift. And you go, okay, that's nice for the primary years, that's just 1 year level, but similar changes in year 8 and regarding the different changes to linear equations changing from year 9 to year 10 down to year 8. And yet they're all really fascinating changes. And so then I'm going, oh, there's so much that I could have explored. But to me, I went back to some of the curriculum descriptions in version 9. And one of the new additions in version 9 is this idea of mathematical processes. And mathematical processes, and I'll just take some time to read it, refer to the thinking, reasoning, communicating, problem solving and investigation processes, and that ACARA hopes to develop these in a more sophisticated way across the curriculum. And this is where the rest of my keynote will go through. An interesting one, the very, very first processes that ACARA emphasises is thinking. And if you were here at the conference last year where Peter Lindenhold looked at building thinking practices and his approach, we can see that this is gaining attention. So I want to focus in on this aspect of a change. So around thinking. So we know that mathematical thinking can have multiple definitions. It can be a way to describe mathematical growth. It can have involve processes and operations. And Peter Lillenhall admits that it can be quite messy, can involve risk-taking, and it can be quite difficult. And I think we've all probably been in a situation where we've given a student a problem and they go, oh no, I just did it. Well, the answer is, I don't know how I did it, I just did it. And so they've got some thinking behind it, but the communication of that thinking is not yet evident. And so we can see from Anna Safard's work that sometimes this thinking process is individualised. It's a self-sustaining process and a form of self-communication. And sometimes that self-communication can be quite challenging to communicate to others. So that's where I'm interested in, is how we communicate our mathematical thinking to others. Go back. So let's start, okay? We're all, when coming up with this problem, I was like, well, what kind of problem do I give people who are doing maths all the time? So I didn't want a problem that you might have been familiar with, but a problem that does evoke thinking. So my question is, how many people are in the room? How do you know? And can you share your thinking with some others around you? All right. Anyone willing to share? And given that we're in a room where people at the back may not be able to hear people at the front, does that really make sense? People at the back may not be able to hear people at the front. If we can just be aware of being quite loud if we're going to share. Anyone wanting to share how they determine? John? Yep.
I go to this lovely group of people up there and then just imagine their faces on this group of people up the back. And you counted those clusters and I counted them as 9, which I may have done incorrectly, I'm not going to check. But I then counted 8 groups of those, so I thought about 72.
Okay. All right. Anyone else wanting to share? Beck.
I went 6 rows back, 1, 2, 3, 4, 5 rows, 5 groups across, and about average of 3 persons per row.
Okay. All right. Anyone else? Brave enough? Helen?
I counted over there as well, and then I thought, if that's I went for 10 over there, and then I thought, that's probably about double there, and then so I took them as my starting point, and not actually put them on, but by comparison, comparing, and I reckon about 65.
All right, so that's what I'm interested in, and that's what I'm currently researching, is how people communicate their thinking and what kind of processes they engage in. So I'd like to share some of that research that we've been doing with a range of students. And now, interestingly, I was more interested not in the answer, but how did you know? And how are you working it out, and the ways of getting to that final thinking. All right. Just have a reflection. How do you feel about communicating your mathematical thinking to others? Maybe think about on that question. But what about some of the questions that you might have seen yesterday? Imagine if you had to do that thinking. How would you feel maybe on an unfamiliar question? It can be quite overwhelming. It can be quite scary. And for our students that we're teaching, that's the kind of feelings that they encounter. So the study that I'm going to share, there's actually 3 studies I'm going to share today. There are some student perspectives, and when I say students, there's some primary perspectives and there's some pre-service perspectives. And with a couple of colleagues, Beck and I have gone into classrooms and done some observations around mathematical learning experiences and how students are communicating their thinking and engaging in mathematics. We are then looking at how a shift in practice can then promote and develop thinking, and then do some more observations. So in the green boxes, that's what I'm going to be sharing today. So the first study was a small, in a regional South Australian school. And when I say small, it's got 36 students. It's got 2 classes. There's a reception year 1, year 2 class, and a year 3, year 4, year 5, year 6 class. So a junior class and an upper class. There are the principal, and there are quite a few teachers, but there's 2 equivalent full-time teachers. The first person I'm going to share is a male from year 5. So whilst there was 36 students, only 23 had consent to participate. So I'm sharing the children that had consent, and you can see the distribution of participants. That there was actually, whilst on the screen it says there was no year 3 males, there was actually no year 3 males at the school. So it's just, that's sometimes how small these places can be. All right. So to help me unpack how students are communicating the thinking and the processes that they engage in, I had to do a lot of reading. I had to think about what actually happens in the classroom, because sometimes what happens in a reading doesn't always happen, or what it looks like in a classroom can look differently. So then we came up with this conceptual framework, and it's just a framework to help us identify the different processes of mathematical thinking, and it's a way to then look at where students are at and how we can then foster and develop that further. So there's got 3 elements. The first element is types of thinking. The second element is the mathematical thinking processes, and the third element is modes to communicate mathematical thinking. I'm going to unpack each of these, and then I'll show you examples of what this looks like in the classroom perspective. So for me, when I went to look at the types of thinking, we could have looked at logical thinking and strategical thinking and all the kinds of thinkings that are out there. But for me, I went back and visited an old friend, and I say an old friend, I don't really know this person, but I've read his work, and you might be familiar with him. It was De Bono, the guy with the 6 thinking hats, but he also wrote a really cool book around practical thinking. And so I'll share what he says about thinking in general. For the mathematical thinking processes, I went into the New South Wales Education Standards Authority and the Queensland Curriculum Assessment Authority, because they had really nice descriptions around communicating mathematics and thinking. And then for the modes of communicating mathematical thinking, we did an extensive literature review of how people communicate mathematics. And if you're communicating mathematics, then you're often communicating thinking. And I haven't listed all of the references, but these are just some of the people who are contributing to this space. So you've got Amy McDonald from Charles Sturt University, you've got Shelley Dole, you've got a whole lot of people there, all right? So then what does this actually look like? So for types of thinking, De Bono starts to describe the types of thinking as a carry-on thinking. If I say, and there's often two responses to this, 2, 4, 6, 8, who do we appreciate? Maybe. You're carrying on my thought. You've identified a pattern and you're carrying it on. You might say 2, 4, 6, 8, 10, 12, 14, 16. You have identified a pattern and you're carrying it on. So that's one type of thinking. Another type of thinking is connect-up thinking. And connect-up thinking is having two distinct ideas and trying to connect and make a relation to them. So if I have a square, I could say that a square has 4 sides, and I'm looking at the property, and those 4 sides have to be equal. So I've got something about side properties, but then I've got the angle properties, and I could say that I've got 4 right angles. So I'm connecting side lengths and angles to connect up to make a square. And there's so many examples of connect-up thinking. But sometimes when I'm connecting up thinking, I don't always have the mathematical terms or language. And I sometimes use these filler words, or what De Bono referred to as porridge words. Now for me, a porridge word in mathematics, one of my, I don't know if it's a favourite or just a word that sort of grates me, is sum. I'm doing my sums. And often students will say, I'm doing my sums when they say 64 divided by 8. Like, it's not a sum. Okay, so that could be an example of a porridge word, all right? And you might have encountered a whole lot of different porridge words. De Bono often describes thinking that can be jump ahead. Think of maybe a Pythagoras theorem problem and you go, do I have to put the C on the left-hand side? Am I working out the C or am I working out the shorter side? Oh, now I know and I get the answer. So I've jumped ahead and I've recognised that pattern, I made it, I've connected what I needed to do, but I've just jumped ahead, because I'm familiar with that process. And then all types of thinking require commitment to action. I must be committed to engage and do. So De Bono was actually really helpful in identifying the different types of mathematical thinking that the students were engaging in. From the thinking processes, the MASA, the New South Wales Education Standards, and the Queensland Curriculum Assessment Authority cognitive verbs descriptions helped in this. When I'm engaging in thinking, I'm often representing something. I'm showing. When you were counting the number of people in the room, there were so many gestures. You were representing your thinking in a visual form. I often describe and explain. And a blatant plug here, Helen Booth and I will be doing a session on describe and explain and the differences between the two at the end of today. But I am using appropriate language and terminology. I am using appropriate symbols, notations and conventions, and I'm using appropriate diagrams, graphs and conventions when I'm communicating my thinking. Now, just have a think back to when you were going through how many people were in the room. How did you communicate your thinking to others? Just have a little quick share. If you had to describe the modes or the methods of communications, what methods did you use? Gestures, pointing, verbs, words. Yeah, okay. Our literature review identified actually 10 different types of ways to communicate your thinking. All right, in no particular order. There was a verbal. Okay, I think we agree that verbal and written and symbolic are probably the most common forms of communicating in mathematical thinking. I have gestures, okay, the slope of the line. We use gestures all the time, and they can often emphasise our communication of an idea. And sometimes we use gestures in a way when we don't quite have the words, but we're trying to get the words, okay. Play, and you might go, oh, okay, that's just an early years thing. But when, thank you, Tiani, no, it's not. We often play a lot in mathematics. Think about exploration through a whole lot of technology. Pictorial and graphical. I've distinguished the difference between those two because graphs are like your sector graphs and your pie graphs and all kinds of graphs. But a pictorial representation, it could be a drawing or if I'm drawing the people in the room, okay, who knew? Someone might have done little stick figures. You've done a pictorial representation. I could use manipulatives or concrete materials. There's written, there's using technology, and go, okay, there's one more, I can't think of anything. But most of the time, thinking can be invisible. I did it I don't know, I just did it. I don't know what the answer is, I just did it. And so we have to start unpacking that invisible thinking. So this is the framework that we've used to help analyse how students are communicating their thinking, the types of thinking that they're using, and their processes. Because if we know this, then we can develop that thinking further and hopefully develop that conceptual understanding. So that's a whole big framework. I'm not going to be able to focus on everything in the next 35 odd minutes. So we're just going to look at some examples of some porridge words from a child and some invisible thinking, but we'll sort of revisit a whole lot of the framework. All right. So just want to emphasise this idea of porridge words. It's generalised language, it's emerging language, it's language of, I really don't know how to describe it, but I'm trying to describe my mathematical thinking. And it allows us to continue our thinking processes. It's like an enabler of our thinking, all right? And they actually have a huge role to play in communicating our thinking. All right, so the research that I'm sharing, there's a commonality between it all. There is drawings. I'm a very qualitative researcher, even though I do a lot of, I know mathematicians love quantitative stuff. I love quantitative stuff too, but I've just found the qualitative data is really quite rich. So participants are asked to draw a picture of themselves doing mathematics. For the younger students, I say, close your eyes, imagine yourself doing mathematics. Once you've got something in your head, then I want you to draw yourself doing mathematics. A couple of criteria, they have to include the head, and I say, make sure your head's big enough so I can see your face. You can use words, numbers, symbols. You can say I've done this over 300 times. Words, numbers, symbols, thought bubbles, and it could be any type of maths, and other people could be in your drawing. So then they're asked to write about their drawing, and to avoid that misinterpretation that can happen in qualitative research, we engage students in an interview. We ask all kinds of interesting questions, and one of my favourite questions is, if maths was a food, what kind of food would it be? Okay? That's another story. That's another keynote of all the different ways that children describe mathematics. So, to code this data, I suppose this is the researchy part of what's happening. We look at a systematic analysis. We code each item individually, then we code it as a collection, and we look at emerging themes and interrelating themes. So, D1. D stands for the school. This is a fourth school, and 1 is the first child at this fourth school that I've done this approach with. He's in year 5 and 10 years, 6 months. Just want to have a think about the different modes of communication this child's using, and maybe just have a chat of what modes, those 10 modes, can you see in this child's drawing? So I'm hoping he's done some written. He said, I feel happy because I figured out a math question that is very hard. So he's written. He's used a lot of symbols. He's got some parentheses or grouping symbols. He's got the multiplication and equals. He's got, a graphical. He's done like a pie chart. And then he's actually done a pictorial representation. And so when we value ways of communicating mathematics, we can see a lot of thinking that's happening behind this. But then when we ask him, we see a whole lot of other modes of communication forming. So I'm going to share a bit of an interview transcript. This comes about halfway through the interview. We revisit part of it. So I ask, can you tell me about your drawing? And as I read through, I'm just going to make some connections to the framework. So my drawing is me working on a maths question that I didn't understand that was in a math mental book before. But now that I've understood it, when I first got the question the first week that we had maths, I got a question like 37 times 5. And I had no idea how to do that. But then I figured out that I needed to break the numbers in half. I had to break the 30 away from the 7. What porridge words can you see just in that first bit? Half, yes. So we often mean half as divided into 2 even groups. But he's using this half to describe partitioning this 37 into 10s and 1s. He's got this emerging language happening, all right? So he's trying to communicate his mathematical thinking through the use of porridge words. And we can understand what he's trying to tell us, but his mathematical language is developing. So I say, yes. You notice that I don't try and intervene too much. So I just let the child speak for themselves. So I have 30 and I have 7, and he's doing this. I have 30 and I have 7. The number which would either be 5 times that number. Yes. So then 5 times 30 would be, I would take off the 0. Take off? I'm not taking off an aeroplane or firing a rocket. He's taking off, so he's subtracting. Okay? I would take off the 0. Then it would be 5 times 3, 15. Then I will add the 0 on, which would be 150. I'll write that down in the first box, and at this point he's pointing to that speech bubble that he's got happening. Then I'd do the unit, which would be 7 times 5. Then I would add whatever that number is to the other number to get the answer. Now, just to go back. All right, so he's trying to explain a question. Now, it's not the question exactly in that speech bubble yet, but he's trying to explain what he's done and record those processes. And in doing so, he's used a whole lot of porridge words. And the last thing he starts to say is, and how do you feel about that strategy? I ask him. I feel it's a very good strategy to figure out big numbers times a little number. All right, so we can start to see a whole lot of porridge words to help him continue his explanation and his communication of mathematical thinking. So figured out, break. I don't actually physically break a number, okay, but we've got this idea of maybe chunking or partitioning. I write it down in that first box. I've got the bigger number and a little number. And so in this way, De Bono describes these porridge words as helping mathematical thinking progress, and it's an intermediate impossible. He hasn't quite got there yet, okay? He's got the conceptual idea, he's developing that conceptual idea, and he's described what he's done, and he's developing his explanations. So then, to continue, if I would start to look at this, he's done some connect-up thinking. He's looked at taking a number and partitioning it to be able to multiply it by 5. So he's connected that 37 has some 10s and some 1s. It's got 33 10s and 7 1s. And then he's trying to then connect off this process. So he's doing a lot of connect-up thinking. And then to continue with this, he refers back to the one that's actually in the thought bubble. And he says, I think this one I struggled with was a speech bubble with the times in it. It uses brackets, which are usually in lines equals. So he's obviously been given a scaffold where there's a line drawn, a symbol, and a line, and it's encased in parentheses or grouping symbols. Okay, so he's talking about the line equaling something, so that blank space in his drawing. And to actually make it my own way instead of nothing. So he wanted to try and attempt it, so he's got a commitment to action here. He's committed to that thinking processes to engage. So instead of doing nothing, he's made that commitment. I could see you trying to do this. Do you want to explain how you did this? So how I did this, I would say the maths question would have this all set up. It would have the question equals bracket 9, bracket, 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 and you can see the brackets when you look back at his drawing line. And then I would have to take off the 5, the 45, and I would put the 5 down in this box. Then I would do the 6 times 5, which would equal 30. And then I would put the 40 in this box. So he's describing this process of multiplication. And then what we've done further is to classify the different types of connect up thinking. He's actually done some noticing and attempting and correcting. And so then he says, which I think I might have got wrong. I actually did a 5 there instead of 6, so that might be a bit wrong, making reference to his drawing, so he's pointing. So in here, we can see some jump ahead thinking, we can see some gestures, we can see some connect up thinking of noticing and attempting, all right, and the use of porridge words. And so this is actually quite helpful in helping this child communicate their thinking in a more clear and succinct way. So I was also interested in, okay, this was where the child just worked with me on a one-on-one basis, but what did this look like in the classroom? And I want you to think about a class that's got about, it had 18 students in it. There's year 3, year 4, year 5, year 6. Just think about that challenge for a moment of trying to teach year 3, year 4, year 5, year 6 all at once. You don't get extra time to teach them mathematics. You don't get 4 lots of extra times to teach them mathematics. So they did a lot of rotations, and the child that I'm about to show, he is there. The child that's doing this one, he's the one who did the drawing, and his friend. So what can mathematical thinking look like? Sometimes it's that, sometimes it's just thinking, but that's their maths mental books, and sometimes it can be really frustrating. It can just be, I don't know what to do. So he's not committed to the action. But there is some good news. It's not always like this. It can look like this, where they're playing a game. It's like that close to 100 from Joe Bowler's work of using arrays and area models to reinforce multiplication facts. But it can also look like this. So we're gesturing. This is the broken ruler task, where a ruler's been broken off and they have to measure something and they have to work it out. So you can see that it sort of starts off, I think it's about 3 centimetres, and then it has a section that breaks off. So this child is communicating his thinking by trying to point out and look at the increments. Okay, he's then counting on his fingers. He's then trying to figure out where it's at. But we could also see, we're just continuing with this. This is just from one video of a moment in time that was in this class. There's actually 4 other students and he's working with the teacher. But he's gesturing, he's then writing down, he's just checking, and he goes, no, oops, I've done a mistake, I don't want anyone to see. He's covered it. And then he starts to erase and fixes it. Someone comes and helps him, so a peer comes to help him. He redirects, and then the teacher also comes and helps him, and then he gets a manipulative in the form of an eraser, okay? So a concrete material. So when we start to look for it, students are communicating their thinking in a variety of ways. We just have to tune into those ways, because then we can actually see their conceptual understanding. All right. And so this broken ruler task then led to this other collaborative task where they had to roll the dice, draw a line to represent the number of centimetres on that dice, and the idea was not to intersect each other but get from one corner of the piece of paper to the other corner of the piece of paper. So there was a play element. So when we start to think about all the aspects and different kinds of mathematical thinking, when we tune into it, we can then notice it and then develop it more. So these kinds of tasks were developing the different forms of communication, but that representation aspect and that ability to describe and explain. But also when you think about that MASA, the processes that are involved, it starts to think about using appropriate conventions. You think about, well, how do I record a length measurement? I need to write centimetres afterwards. So there's a whole lot of thinking that was going in there. So that was one study. A second study, we continue with School D, and that should actually be School F, where we've got some research funding from the Margaret Trambath Research Association and looking at the early years. So that was in the upper primaries, and we were interested, is it the same in the early years? And when we call early years, we are looking at reception to year 2, and we've gone back to School D and just looking at the 16 students in reception to Year 2, and we've looked at another school where it's reception to Year 1 and it's 15 students. And so the students did the same kind of thinking task. This is a child from school D, and the same kind of prompt, and he's done me and my friends learning about symbols, okay? And then they were also given a thinking task, and this thinking task was co-designed with the teachers. It was done early term 1, and so we had to try and choose a thinking task that students would be able to achieve and show understanding. And so we looked at this in conjunction with teachers, and it was a number chart, and it was a partial number chart, a number chart that went up to 500. This was a number chart doing skip count. This child was in Year 2, and so this starting at 5, skip count by 5, and identify the numbers. And we thought, okay, great, they'll be able to show their thinking in a variety of ways. This is what we got. We got 40 and 100 and whatever it is, the right numbers. And I go, well, how did you do that? So if we just collected that as evidence, we could say, yes, okay, tick, you got it right. But if we're really interested in the thinking process of how they got there, was it just by chance? Because we don't know until you're asked. But when we started to ask the child, we could see their explanations. They didn't want to write, how do you know? Okay? And similar, this is one of our favourite children at our school. This is him drawing maths. Now, last year's picture, he did himself in a sheep shed. This year, he's building a kitchen table. Okay, that's him doing maths. He's a fascinating child. I said, can you write about your drawing? He goes, yeah, it's blah, 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 blah. That's his blah, 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 blah. That's what he said. So anyway, but his thinking task, if we just look at that, he's got the numbers, but they're in the wrong spot. So how has he approached it? So we had to unpack that thinking. And another child, we start to see, and this was a common thing, I know because I learnt it. Okay, so the thinking's still invisible here. I know it because I learnt it. I learnt how to skip count by 5s. Okay, but when we unpacked this and did this with children, it was interesting how students were skip counting by 5s. Some would go 5, 10, 15, 20. Some would go 5, 10, 15. So it was different ways of skip counting. Some were quite comfortable in using their fingers. Others did the dodgy under the table thinking. Or you could see them going, I don't really want to use my fingers, but I'm using my fingers. So it's interesting when you start to unpack how they are thinking to get the answer. So we're really interested in that process of getting to the answer. So then what we're also interested in is whether these kinds of things are just a child thing, or is it a everyone thing? And so what we're looking at, and what I'm about to share now, is whether porridge words and these whole thinking processes and the framework can be applied to other people. So what I've done is look at pre-service primary teachers who are taking a mathematics education specialism. This is a second year course in a 4th year degree, and I coordinate the second year course. So they've done one specialism, and the course that I look at has a measurement and geometry focus. Okay. In this course, we have a variety of assessments, and one assessment is quizzes, where students are given 3 lots of quizzes. They're given a sample quiz to practice, because we know when pre-service teachers come in, and I'll share some of the drawings in a moment from them, so you get a snapshot of the kinds of teachers that we're working with, that they get a sample quiz, a practice quiz, and then they get a quiz that's counted towards their assessment. So this is just arranged. So same thing, okay, so the drawing process can be applied to adults as well. Draw yourself doing mathematics. This one student did himself doing DJing, okay, he could see so much maths in his DJ work. Another student, sometimes I fly and sometimes I feel like I'm drowning and about to be chased by a shark. Okay, so that's what she felt like when she was doing mathematics. Another student says, in maths, I feel angry and annoyed when I don't understand, but when I finally get it, I feel proud and excited and I enjoy the maths journey. So we can see there's a whole lot of drawings, and I could just share all the different drawings that the pre-service teachers have done, but we get a snapshot of the group of students that we are working with. And so in the quiz, we are given questions that are often at the primary years, but sometimes just go a bit beyond the primary years because we want the students to have that understanding of where maths can link to. Just like yesterday where Bronwyn showed us the partial differential equations, just where we know where maths can lead to. So while sometimes the questions may be primary focused, sometimes it's junior secondary. So one of the questions that we gave in our quiz was find the area of the composite shape. 10 meters is the total height of the shape. And they get marks for obviously communicating their work, but they also get marks for their explanation of mathematical thinking and showing all their work. So just have a think, share with other people, how would you go about this question? Now, I do hate interrupting mathematical conversations, but I am going to interject. When I created this design in GeoGebra, I created it as 2 semicircles, a triangle and a rectangle. That's how I saw it, okay? Then 2 semicircles, the triangle and then the rectangle down the bottom. I then removed some of the lines and did things like that. And it's interesting because what we do with the quizzes is we get students to share their processes so that they can see and appreciate different ways of doing mathematics. So I'm going to share some of their responses and then think about, well, how can we apply the framework around the types of thinking, the processes and the modes of communication in this. And I'll just give you some examples. There was one that just gave me the tink, you know, you just go, oh my goodness, I never saw it that way. And then you go, no, I can't not see it that way. So it's interesting how when we start to share, I know. All right, so one student felt very confident. She just laid it out very symbolically, very algebraically. There's symbolic and algebraic explanation, but there's no real explanation of why or how she's done it. And when we talk about explanation, it's the why and the how. Okay, so she's sort of just gone through the processes. All right. Another student said, I first partitioned the composite shape, okay, into smaller shapes and numbered them. I turned the semicircles into a whole circle and both triangles into one. So she saw initially 2 smaller triangles, as shown. I followed each of the specific formulas to solve. So she's starting to explain the process of what she's done. So I ensured to subtract 8 meters because that is not included at the base, and then she's tried to work it out. Okay, so we were interested in the explanations because we know when it comes to teaching mathematics that sometimes explaining the mathematics and the how and the what and the why can be really challenging. So that's what we're trying to foster here in the quizzes. We just don't want them just to do mathematics. We want them to be able to explain what, how and why. Describe, explain, anyway. All right. So then we see another one. To begin to solve this question, I divided the composite shape up into smaller regular shapes, labelled them. I've got the areas of 1 and 2, then the areas of 3, then the areas of 4, and then she's described how she summed them all up. So pretty standard, circles, triangles and squares, or circles, triangles and rectangles, depending on how the students have seen it. Another one, similar process, but we can just see the differences in the language, and it's really important to focus in on that language because just think back to the drawings, the shark girl, okay? or they go, sometimes I like it, sometimes I don't. They're not always confident in communicating their explanations. So we're trying to develop and share that, okay? And so we can see lots of pictorial representations here of the base of the triangle is, and to make the rectangle, and then she's divided into a square. So when we actually appreciate different modes, we can start to see and value that. Another typical example, okay, so they could either do it handwritten or using Word or whatever version that they felt comfortable with. But this is the one that I was like, duh, you know how you just never see it? No. Okay? You did it that way. I was just like, oh, yeah, I got so excited. Okay? No real explanations of why she's done it that way, but she's just described and outlined what she's done. Okay? So it's just interesting. And so we get pre-service teachers to share their processes. There's some errors in the math, okay? We get that, okay? But if she actually if it wasn't a calculation error, the process can still work that way. So I wanted to ask a couple of questions. And that one is, how do we communicate our thinking to others? And what opportunities do we provide our students to communicate their thinking to others? And what methods do we prioritise? I just have a think about your own practice. What opportunities do you give? And you might just have a quick chit chat.
Give time for students to engage in the thinking and then give them the opportunity to communicate their thinking without the interruption, because it's often that process of, as we are self-talking something through, we make those connections and those discoveries and realise, no, that's not clear enough and I need to readjust. But time's a big one. If we don't give time.
So for those who may not have heard it, Helen was talking about time and giving students the opportunity to have that moment to be able to share. But it also comes down to the teacher questioning. Often we're just interested in the answer and not how we get there. And we see that in the research that we're currently doing, where the classes have a teacher and a student support officer and SSO in the room, and the types of questions that are different between the two people. The teacher often asks, not always, but starts to ask, how do you know? But the SSO hasn't got that practice yet. So we have to value the kinds of questions and then give them the time to be able to formulate and show. Yeah. So for me, I was always interested in, well, how do these modes fit? And to me, I know sometimes people don't like the jigsaw analogy in mathematics, but I carefully created this jigsaw, and I want to explain the nodes and I had the jigsaw language and now it's gone. There's actually the U's and the nodes, let's call them that. I'm getting cranky with myself because I know they've got names. They do fit together, okay? But the way that they can fit together can constantly look different, all right? I don't think there's one set way that these modes of communication fit, all right? I don't think there's necessarily one configuration that is better than the other. And sometimes what we'll hope is that the invisible thinking does drop out. But they can be all interconnected and be joined in multiple ways. All right? So this is how we are trying to emphasise that if we emphasise the different types of mathematical thinking and the modes of communication, then we can see it in our students. And that sometimes if we just collected that one piece of written work sample, we're missing a whole lot of information. So we know that communicating mathematical thinking is multifaceted. And I just want to briefly return to the work of Di Bono and this idea of that intermediate impossible. Sometimes thinking is impossible in that short term. But with time to help you process your own thoughts, to try and then blurt out maybe the porridge words, it then facilitates that mathematical thinking. So he describes this intermediate impossible as an idea that is not right, but acts as a transitional point to another idea that is right. Or you can almost substitute that of the porridge words help flow the mathematical thinking. So that intermediately impossible. And I think we've all been in that situation where you go, oh, I haven't done that math for a while. I need to think about it. No, I'm not ready for it. Okay, now, yeah. Oh, now I can see it in a different way. And so we all, I suppose, have experienced this idea of intermediately impossible. So we suggest that invisible thinking that can often happen is a sign that students are hunting for mathematical clues to help them explain their mathematical thinking to others. So it doesn't matter whether they're reception year 2, upper primary, pre-service teachers, us, secondary students, we are hunting for our clues, okay? And so sometimes there are clues that are obvious to everyone because we've been exposed to the mathematics. But can often still be misinterpreted. Okay, and we saw some of those misinterpretations in some of the pre-service teachers' explanations. Okay, and sometimes the clues can be features that are obvious to everyone, but do not become clues until some kind of significance is attached to them. So you know how you sometimes in a class and you go, everyone gets it, but I don't. I need to put some significance to it. I need to understand it in a different way. Ah, now I see why it's important. I then can help process. And sometimes clues that are not at all obvious and have to be worked on. So when trying to unpack this, De Bono does suggest that we are on a clue hunt. I'm going to have to do there we go. So we touched on some of the implications already. Mathematical thinking is multimodal. And I suppose we need to value that multimodalness. That's a word. Kate might have just invented a porridge word there. But we need to value that multimodal approach. And we need to think about our assessments. If we recognise that mathematical thinking and the communication of our thinking is multimodal, our assessments are predominantly what? Written. Sometimes we give verbal presentations, but there's often a written component to that. So then how do we value that mathematical thinking when our assessments are predominantly written, symbolic and graphical? So what can we do? What other approaches can we use? We also need those opportunities to share our thinking. And more importantly, plan for the thinking. Creating mathematical thinking classroom just doesn't happen. We do need to plan for it. We need to plan for our questions that we're going to ask. We're going to go, great, you've got the answer, but how do you know? We need to plan for that. And that planning for thinking can be quite challenging, and especially with some of the schools that we're working in. Planning for thinking. So then, if one of the aims of the Australian curriculum mathematics is to become confident, proficient and effective users and communicators of mathematics, how do we go about it? How do we start to do this? So I just want to share a framework from Herbert and Eisman from 2017. Sometimes that waiting, whilst it can be quite challenging, whilst it being like, they're quiet, they're not saying anything, oh my goodness, have I targeted the right question? Waiting is really important. Waiting to give a question and a response. Waiting depends on the familiarity with a question, or a process, or a mode of communication. I know sometimes that awkward pause can feel like it's going on forever, but we do need that time. We need to have opportunities where we invite students to participate and encourage students to listen and respond to others. And it was interesting in the pre-service teachers where they started to share, they became more confident. It changed the tutorial sessions. It changed what they were communicating in their quizzes. That was one of the earlier quiz questions compared to the last, where they go, I didn't know how, I could have just written pages and pages to explain my mathematical thinking. And sometimes we need to revoice. So either emphasising or restating or extending a student idea, building on, or help with that connect up thinking. Okay, let me help you understand. Did you mean this? Ah, that's similar too. Continuing on this is asking students to revoice themselves. Can someone else say that in another way? Can someone else show me that in a different form of communication? We might want to probe, but importantly, we need to create opportunities to engage with another's reasoning and encourage students to use someone else's approach. So we need those opportunities of those sharing moments, those sharing times, sharing those explanations. All right, there's my reference list. Oh, look at that. Okay. Blatant plug, I am, because you have to, don't you? No? The small schools has been an interesting discovery, an interesting research area that sort of stumbled by chance. I did go to a small school as a child and didn't think much of it. It was just a nice family atmosphere as a school. But I think there's a whole lot of challenges in teaching and learning of mathematics in multi-years. So there is a session at 11:30. And then if you want to understand the difference between describe and explain, there's a session at 1:40. But please feel free to contact and reach out. And I do have homework questions, which I forgot to tell you at the start. But that's okay, so at the end of the lesson, quick homework. I do want you to think, how will you orchestrate opportunities that promote mathematical thinking in your context? All right, be interested to hear and share that. So, thank you.